Let's start with the high-level discussion of the most fundamental concepts, which are concurrency and multithreading. It is my belief that the best way to understand these concepts is by gaining some amount of intuition about hardware. The reason why I think that hardware intuition is important in this context is because I myself came to software development from hardware world. And since hardware is intrinsically concurrent, I had relatively easy time figuring out the concurrency in software. I simply had to apply my pre-existing intuition to various software constructs. And that's exactly the path I'm gonna take you with me now. As you might know, computer consists of many different components. But the central component, the heart of the computer, is its central processing unit, or in short CPU. The very first commercially available CPU was Intel 4004 and it came out in 1971. As you can see, this CPU was packaged in a 16-pin package and it consisted of approximately 2300 transistors. Transistors are small electronic switches that allow hardware engineers to design logic in hardware. So transistors are basically the most fundamental operating units of digital logic. Alright, but it was 1971 and a lot of time passed since then. In year 2000, Intel introduced its series of Pentium 4 processors, and these processors were much more complex. So if you look at the back of this processor, you will see a lot of small yellow dots. Each of these dots is a standalone electronic pin which connects the central processing unit to the rest of the computer. Therefore, while Intel 404 in 1971 had 16 pins, Pentium 4 processor already had hundreds of them. And sure enough, its internal structure became much more complex and it consisted of approximately 42 million transistors. So think about that. If you have enough background in hardware, you can look at the schematics of the first commercially available CPU, Intel 4004, and actually understand its mode of operation, what it does, etc. Because you can actually review 2300 transistors. However, regardless of how smart you are, you can't really review the implementation of Intel Pentium 4 on a transistor level. There are just too many transistors in this processor. And sure enough, after another 20 years of evolution, today our central processing units are even much more complex than Intel Pentium 4, and they already consist of approximately 2 billion transistors. So CPUs are very complex beasts that consist of billions of transistors and have hundreds of modules inside them. But fortunately, you don't need to understand how CPUs are built in details. All I want to achieve in this module is to give you some basic hardware intuition about the mode of operation of CPU and operating systems that will assist you in understanding the concurrency in software. So just keep that point in mind. I want you to have hardware intuition, but I will not try to explain you how CPU and operating systems work in details, and I will oversimplify many concepts to make this explanation accessible and quick. With all these disclaimers in mind, let's start our journey to hardware intuition. How does CPU work? Well, as I already said in the previous lecture, it's a very complicated question, but you don't really need to understand how CPU works in details. What you do need to understand is high-level operation basics of a modern CPU. So, with that in mind, you can think about CPU as a box. And you don't really care what's going on inside this box. What you care about is what's going into the box from outside. In other words, you want to know what's the input to CPU. Well, the input is a sequence of ones and zeros. Each individual 1 or 0 value is called bit. So CPU's input is a sequence of bits. This specific sequence of bits that you see on your screen right now corresponds to a command which says move the content of register BX into register AX. Register is CPU's internal storage unit. So basically this command says move the content of something that is stored in your internal storage to another location. As you might guess, The bits that represent a specific command are not random. There are clear definition of what commands CPU knows to interpret and what it does in response to these commands. Each of the valid sequences of bits that CPU knows to interpret as a command is called instruction. And the total set of commands that CPU knows to interpret is called CPU instruction set. Now, you don't really need to understand what instructions set is or which commands constitute specific instruction set. All you need to understand that there are specific commands that are inputs to CPU, and CPU knows what to do in response to these commands. Now, evidently, one single instruction executed by CPU will not achieve much. Therefore, usually, the input to the CPU consists of many instructions. It's an ordered sequence of instructions, and this ordered sequence of instructions is called machine code. So basically, machine code is a very long sequence of ones and zeros, usually millions of them. And if you try to read or write a specific sequence of ones and zeros that has millions of them, you will inevitably fail. Therefore, machine code is not human readable and it's not human writable, unless we are talking about very simple cases. What we usually do, we write code in some higher level language, and then we use compilers that convert human readable code into machine code. So, at a very high level, CPU is a box, and we don't know what's going on inside this box, but we know that we feed machine code into that box, and as a result of processing of this machine code, CPU interacts with memory and with input and output devices in a very specific manner. And let me say it once again to just make sure that we are absolutely clear on this point. This high-level description is very simplistic and it is not representative of a real complexity of a modern CPU. However, this should be enough for our discussion of concurrency and multithreading. Now that you understand how CPUs work at a very high level, we can start discussing system architectures. And the very first architecture that we are going to describe is called single tasking system. When I say system, I mainly refer to CPU and operating system combination. Operating systems like Windows and macOS and Linux are special kind of software which is designed to take advantage of hardware capabilities and expose them to third-party applications, our applications, in a convenient and performant way. So whenever we talk about a system, we really need to consider both the hardware and the operating system. However, the exact separation of responsibilities between the hardware and the operating system is not that important to us. All we need to know is that both of these components are required to make a modern general-purpose computer work. So, single tasking system simply executes the machine code of one single task until that task is terminated. I know it doesn't ring a bell right now, but let me show you an example that will clarify what I mean. Let's say that we've got the machine code of one single program, and this machine code is submitted to the CPU for execution. So CPU starts executing the instructions from this machine code one by one. And to keep track of the execution, CPU uses what's called program counter. That's simply an internal pointer inside CPU that says I currently execute instruction number X. So CPU starts executing one instruction and another instruction, and it doesn't have to execute these instructions sequentially. It can jump around in response to special kind of instructions, for example, branch instructions. At some point in time, program counter will point to the last instruction in the program, and then after that the program is considered terminated. So we can say that at some point program counter points to the last instruction in the specific task, after which the machine code of another task gets executed. As long as a single program is loaded into our CPU, no other program can run, and the CPU becomes fully dedicated to the execution of that one single program. The benefit of single tasking system is that it's relatively simple. It just executes the machine code of one single program at a time and shouldn't be concerned with anything else. But that's also the downside, because whenever that program, or should I say that task, executes, it takes full ownership of the entire CPU. So for example, now you are watching this lecture in your browser or maybe through application on your mobile phone. And in a moment, you would like to switch and check your Facebook or maybe your email. On a single tasking operating system, you would need to completely shut down the browser or your application and switch to another one. This doesn't sound very convenient, isn't it? And in fact, it isn't. Therefore, I don't know about any general purpose operating system today which is single tasking system. And maybe the last widely used single tasking operating system was MS-DOS. So if these systems aren't used, why did I discuss them with you? Well, I wanted you to have some baseline understanding of very simple system in order to be able to contrast it with multitasking systems that we will discuss in the following lectures. Now we can start discussing multitasking systems, and the very first type of multitasking system that we are going to discuss is called Cooperative Multitasking System. So in Cooperative Multitasking System, individual tasks that are being executed right now can release CPU resources by yielding. And yielding is a special kind of instruction. While they yield, these tasks will release the CPU resources and other tasks will get a chance to be executed. And the general intention, the difference between yielding and termination, is that tasks that yield are expected to be resumed at a later stage. So even though tasks yield, they will get a chance to proceed with the execution at a later time. Alright, just like before, this probably doesn't ring a bell, so let's see an example. Let's say that two tasks should be executed by our CPU. It starts executing the first one, jumping between different instructions. And at some point of time, program counter lands on yield instruction. When that happens, CPU looks for other tasks that need to be executed, and it sees the second task. So it switches to executing it instead of the first task and starts running on the second task. At some point, program counter points to yield instruction in the second task. So CPU once again looks around and sees whether there are any tasks other than second one to be executed, and it sees the first task. So it switches back to the first task. But this time, instead of starting the execution from the very first instruction in the first task, program counter points to that same instruction that yielded the first task before. So basically CPU resumes execution of the first task from the same point where it left. And you can imagine that if at some later point in time first task will yield again, second task will get a chance to run. And you can extrapolate that to more than two tasks in your imagination and see how when different tasks yield, if CPU is kind of fair, all of them will eventually get a chance to run. So that's cooperative multitasking execution. Each individual task is responsible to yield at some point to release CPU resources to other tasks. The benefit of cooperative multitasking is that it allows concurrent execution of multiple tasks. And concurrent here means that if tasks yield relatively often, let's say 100 times a second, which is not that much in terms of CPU timescale, then all of them will get a chance to run eventually. And from the outside, over the span of a second, let's say, user can get a feeling that 100 tasks run in parallel, while in practice it's just one single CPU switching between execution of different tasks relatively often. The downside of cooperative multitasking is that concurrency in this mode of operation is predicated on cooperation between all the tasks. In other words, Just one single misbehaving task can make the entire system unresponsive by claiming CPU resources for a very long time. An example of cooperative multitasking system will be Windows 3.1, and it indeed suffered from this problem of programs not yielding often enough and thus making the entire system unresponsive. The next type of system on our list is called Preemptive Multitasking System. In this type of system, it's operating system that manages CPU resources. Basically what happens in preemptive multitasking systems is that operating system says to individual tasks, now it's your turn to run, and at a later time it pauses these tasks and give another task chance to execute. In some sense, it's very similar to cooperative multitasking systems that we have already discussed, but instead of tasks managing CPU resources by themselves, this responsibility is now delegated to higher level operating system. And as usual, example will clarify it much better in my opinion. Just like before, we've got machine code of these two tasks, and CPU starts executing the first task, jumping between different instructions in this machine code. At some point of time, operating system will decide to pause this specific task and switch execution to another task. In contrast to cooperative multitasking systems, this switch of running task is not related to the task itself in any way. It's the higher level operating system that decides, okay, now you are paused and another task starts to execute. So the second task gets executed, and at some later point of time, operating system will say, alright, now you are paused and I want to schedule another task to run on the CPU, and it will switch back to task number 1. And you can imagine how it works long term with operating system basically switching between these two tasks very rapidly, thus making it appear to the external observer like two of them are executed at the same time. And you can even imagine how it scales to multiple tasks, and if operating system indeed does a decent job and switches between different tasks in a fair and timely manner, then you can see multiple tasks being executed in some predefined period of time, even though it's just one single task running on the CPU at any instant of time. The advantage of preemptive multitasking is that it allows concurrent execution of multiple tasks, just like cooperative multitasking system, but in addition, it also guarantees that system remains responsive irrespective of what individual tasks do. So, for example, you might have a poorly written program that contains infinite loop, and this program wants to claim the entire CPU to itself for eternity. Such a program would make cooperative multitasking system unresponsive, but in preemptive multitasking system, even though this program runs indefinitely, operating system ensures that other tasks concurrently with this one misbehaving task, that other tasks also get a chance to run. So to the external observer, it appears like all tasks are running at the same time, even though there are only one task running at any given instant of time, and one of the tasks is really misbehaving. The downside of preemptive multitasking systems is that they are very complex and very difficult to implement. It is this ability to schedule different tasks on the CPU and switch between them whenever the operating system decides appropriate that makes it really complex. But the good news are that this complexity is largely abstracted out from us, from application developers, by operating systems. Therefore, in most cases, if you don't work on operating systems themselves, then you don't need to deal with this complexity at all. And since preemptive multitasking is such a nice concept that ensures systems responsiveness irrespective of the behavior of the individual tasks, it's very common in general purpose operating systems today. In fact, I think that all the operating systems that I know about employ preemptive multitasking. And what's relevant in the context of this course is that Android is also preemptive multitasking system. So on Android, when you execute multiple tasks concurrently, it's the operating system that decides which of the tasks run at any given instant of time. Another type of systems which became very popular in the past, say, 20 years is called multiprocessing system. Simply put, multiprocessing system is a system with more than one CPU. And basically, as of today, most consumer phones and PCs are multiprocessing systems. So, how does multiprocessing system work? Well, at a very high level, we still have this box of CPU, but inside this box, we have multiple CPUs. And since we can have CPU inside and CPU on the outside, the internal CPUs are called cores. So we've got CPU which consists of multiple cores, and each core processes its machine code and interacts with memory and I/O devices in an independent manner. However, having several cores in a single CPU requires very delicate orchestration of work. So these cores are not entirely independent of one another, but they communicate in a very complex manner to make sure that everything stays coherent and nothing gets out of sync. And just like before, this explanation is very simplistic. In reality, multi-core CPUs are very complex beasts, and the fact that there are multiple cores inside one CPU gives rise to very difficult technical challenges that engineers need to address. However, just like preemptive multitasking, multiprocessing is largely hidden from application developers, and we don't need to think about it. So you don't need to understand multi-core CPUs in more details than that. So what's the benefit of multiprocessing system? Well, it allows for true parallelism. And now you might ask yourself, well, we've been talking about concurrency and now we talk about parallelism, and what's true parallelism if the concurrency is not true? Well, I'm glad you asked. Let's talk about that. Concurrency is when multiple tasks appear to make progress during the same time period. For example, you take preemptive multitasking system and you feed into it, let's say 10 tasks, and you watch what happens over a period of 1 second. So after 1 second, all of the tasks made some progress, and it looks like this system runs them at the same time. But you already know that preemptive multitasking system might run just one single task at a time. It simply switches between different tasks very quickly. However, as long as it looks like all these tasks are executed simultaneously, we are talking about concurrency. Now, parallelism, in contrast, is when multiple tasks make progress at the same time instant. In other words, tasks truly run at the same time. Now, one interesting thing to note in this context is that parallelism is a special case of concurrency. All parallel systems are concurrent. However, not all concurrent systems are parallel. Furthermore, individual CPUs in multiprocessing system, which supports parallelism, usually also support multitasking. So you've got multiple CPUs and each of them switches between different tasks and they work at the same time, and this interaction is very complex. And who manages it? Well, operating system does. And that's really handy because as long as operating system does its job, we don't really need to know whether the system is multiprocessing or not. We can just concentrate on concurrency, and if it's also parallel, then operating system will take care of that and it will distribute the load in a performant manner for us. And this is actually a very complex and tricky point. However, I don't really want to go into it in depth. Just remember that you don't really need to know whether the system is parallel or not. All you need to know is that it supports concurrency. However, if you're really interested and you really want to understand these concepts in more depth, I will attach a link to this lecture to a great talk that will explain you the difference between concurrency and parallelism in much more details. Alright, I started this module by claiming that it will be much easier to understand multithreading if you have some amount of hardware intuition. And in my opinion, by this point, you already have enough hardware intuition to really loop it back and tie everything together and bring us back to the topic of this course, which is multithreading. So let's talk about processes and threads in Android. What's process? Well, in non-multitasking system, in single tasking system, there's just one single task that corresponds to the only running program. In fact, you can even say that the notion of task is irrelevant to single tasking system because there's just one of them. Now, in Android, which is multitasking system, each running program application gets its own task, and this task is associated with isolated execution environment, and we call this isolated execution environment sandbox. So each application has a standalone task and it has a standalone sandbox, and together the task and the sandbox constitute application's process. And an immediate corollary from the fact that Android sandboxes standalone applications is that applications can't access the environment of one another. So one application can interfere with execution of another application, and this sandboxing affects reliability and security of the entire platform. So just to repeat, each application in Android gets its own task and its own execution environment, which we call sandbox. And this task and the sandbox together constitute application's process. Now let's jump to threads. Very first multitasking systems allowed multiple programs to run concurrently in separate processes. So you basically could launch multiple programs and see them execute concurrently. However, each program had just one single task to itself, which was associated with program's process. But very soon it became evident that even single program can also benefit from being decomposed into multiple concurrent tasks. So just like CPU can run multiple standalone programs in different tasks, developers thought that it would be great to have several standalone tasks in a single program. And indeed, in Android, each process can host one or more tasks. And these tasks that are hosted in a single process are called threads. Now, unlike processes, threads aren't sandboxed. So each thread gets its own task, but threads don't get their own execution environment. They inherit execution environment from the parent process. Therefore, this way, threads can easily communicate and exchange data with one another within, of course, bounds of a single process. Let's demonstrate that graphically. So we have process 0, and this process has two threads in it, thread 0 and thread 1. And then we have another process, process 1, and this process can have, for example, 3 threads in it. Threads in process 0 share the sandbox, the execution environment, with process 0 itself, and threads in process 1 share execution environment, the sandbox, with process 1. And for example, threads from process 1 can't access anything inside process 0. So these are different execution environments that we call sandboxes, and each application gets its own sandbox, and within bounds of that sandbox, applications can execute multiple tasks, which we call threads, and these threads share the same sandbox, so they can exchange data and state easily. And that brings us to the main topic of this course. So multithreading is basically the composition of applications logic into multiple concurrent tasks. It might sound not that difficult right now, but as you'll see in this course, it's really challenging task. In fact, multithreading, in my opinion, is one of the most challenging aspects of software development, and we will talk about all of that in the future lectures in this course. This lecture and the following ones will be dedicated to thread class, which is part of java.lang package. Generally speaking, thread class represents single in-process thread of execution, and thread of execution is the same as task. So in other words, thread class represents single in-process task. There are basically two ways to instantiate a new instance of thread. The first one will be to define your own class that extends from thread class. inside your class you override run method and then perform whatever actions that you want to do in this new thread inside this method. Then after you have this class defined, you can instantiate a new object and assign it to some thread variable. The second approach involves runnable object. Runnables are basically containers for code. They just contain some code that should be executed, but runnables do not specify how this code will be executed and on which thread. And then you construct a new thread, new simple thread, and pass that runnable into its constructor. Now you can choose whatever approach you like the best, or maybe you can even combine them. I personally, however, use only the right approach. And the reason for that is because the left hand side, the left approach, is basically demonstrates the use of inheritance. So you basically inherit from thread class and override its method. The right hand side basically demonstrates composition. So you pass runnable object that simply encapsulates some code into new thread class. And there is a general rule of thumb described by Joshua Block in his book Effective Java as item 18 that says favor composition over inheritance. So I try to use composition as much as I can instead of inheritance. However, as I said, both approaches will work. Now keep in mind that instantiated thread object doesn't mean that you started a new task. In order to start a new thread, you need to execute start command. So basically, regardless of how you instantiate your threads, you then need to call start method on your newly instantiated thread to make it actually run. Before you start it, nothing happens. And for me personally, that's actually one of the most common bugs when I use bare threads. I simply forget to call start on new thread and then nothing happens. So if you use bare threads and nothing happens, or at least what you expected to happen doesn't happen, then just go and check that you actually started your threads. And as usual, let me show you graphical example just to make sure that we are on the same page. So we've got a machine code of a specific task, and then CPU starts to execute this machine code, and at some point it lands on this thread.start instruction. When this happens, a new task is created. And once you've got these two tasks, basically what happens is that CPU and operating system in collaboration start executing these two tasks concurrently using preemptive multitasking technique. We have already discussed preemptive multitasking before. It's that execution scheme where operating system says to individual tasks, now you run, no, now you pause, another one runs, etc. So basically, whenever you start a new thread, you simply add another task and operating system picks up from there and starts executing that task concurrently with any other tasks that had been running before that point. Now it's time for you to get hands-on experience with Android threads. So go to exercises package, exercise 1, and open this exercise 1 fragment. This fragment is very simple. All it has is just one single button, and when this button is clicked, count iterations method is being called. This method is also not very complicated. We set up some start timestamp and some end timestamp, which is some predefined amount of milliseconds after the start, and then this method basically loops until we reach the target timestamp and timestamp, and then it prints how many iterations it completed in this predefined amount of seconds. Nothing too fancy here. So let's run this application and see what it does. When you launch this app, you will immediately get to the home screen. Now I have just one single entry, exercise 1, but I guess that by the end of this course you'll see many more entries here, but you need to choose exercise 1. And then you will get to this screen, which is represented by the fragment that we've already seen. And then if you click on count iterations button, then you might see that the shadow behind this button looks stuck, and you wait for 10 seconds and this shadow disappears and the button returns to its original state. And in Locket you can see that we basically have this exercise 1 iterations in 10 seconds and some number. And then you have this message: choreographer skipped 600 frames. The application may be doing too much work on its main thread. Furthermore, if you press on this count iterations button and then you press on back button on your phone and then you wait for 5 seconds, then you will see this dialog. And experienced Android developers immediately recognize it. It's called Application Not Responding dialog, or in short ANR dialog. And at this point you don't need to understand why this dialog is shown or what it means. We will have an entire module about UI thread later in this course. However, what I want you to see is that there is definitely some problem. When we click on this button, application skips a lot of frames, 600 of them, and then if you try to go back during that time, it basically shows you ANR dialog. Not good. Your job in this exercise is to fix this problem. So back to exercise 1 fragment. What you need to do is basically take all the code in this count iterations method and make sure that it executes on a new thread. This will fix all the errors that we've seen so far. Basically, this will fix the freeze of the button and this will fix the ANR dialog. So just take this code and make sure that it executes on a new thread. If you have any difficulties during this exercise, then you can go to Solutions package, Exercise 1, Solution Exercise 1 fragment. This class contains the solution to exercise 1, so you can get ideas from there if you're really stuck. So, good luck and have fun! In this lecture, you are going to learn about garbage collector, which is a very important concept to understand for professional Android developers. However, before we get to discuss garbage collector itself, let's understand what memory allocation is. So let's say that we've got this simple main activity. In its onCreate method, it instantiates a new instance of my object and then assigns that instance into its own internal private field. If we could look into the memory during the execution of this piece of code, we will see something like this. First, main activity instance is created, and then when its onCreate method is called, it instantiates a new my object. So now we have two objects residing in memory. And then that instance of my object is being assigned to the internal private field of this main activity object. So basically main activity now has a reference to my object and can actually reach it whenever needed. So by the end of the execution of onCreate method, we have two objects in memory and we have a reference pointing from main activity instance to my object instance. In general, whenever new objects are created, they consume some amount of available memory. And as you might guess, if you create too many objects and none of them is being removed from the memory, then sooner or later the application will run out of memory. And whenever this happens, your application crashes with this out of memory exception. That's obviously not what you want your application to do, right? Very generally speaking, garbage collector is a system process which automatically reclaims memory by discarding objects that are no longer in use. So the key point here is that it works automatically and that it reclaims memory from objects that are no longer in use. And this description immediately raises another question, which is how does garbage collector know which objects are no longer in use? Well, I am glad you asked. Let's discuss that. To understand how garbage collector works, you need to understand the concept of object reachability. So whenever we look at some specific object in memory, we can ask the following question: is this object reachable? The very first condition to check is whether that object is a root. Now, you don't need to understand what's root right now. We will discuss this a little bit later. What you need to understand is that if that object is a root, then it is by definition reachable. If it's not a root, then we ask the following question: is it referenced by any other objects in memory? And if the answer is no, then basically this object is not reachable. So if the object isn't root and it's not referenced by any other objects, then it's not reachable. Then we ask the following question. Is there an object which references this specific object which is by itself reachable? In other words, we need to run the same algorithm on each object that references that specific object that we are interested in. And this means that we execute this algorithm recursively on all the parents. And if we determine that even one parent is reachable, then this object is reachable. But if no parent is reachable, then this object is not reachable. So if you perform this flow for each allocated object in memory, you will understand which of them are reachable and which of them are not. And what's important to us is that whenever an object is determined to be not reachable, then it's considered to be not in use, and then it is eligible for garbage collection. So basically, garbage collector will automatically determine which objects in memory are not reachable anymore, and then it will release the memory associated with these objects. And let me show you an example. Let's say that we've got these three objects and two references between them. And garbage collector wants to understand whether my object2 instance is reachable or not. So it asks, is my object2 a root? And the answer to this question is no. And again, you don't need to understand what's root object right now. So since my object2 instance isn't root, the next question that garbage collector asks is my object2 instance referenced by any other object? And the answer is yes. So it invokes recursively the same algorithm for the parent. And the parent in this case is my object1. So it asks, is my object1 a root? No, it isn't. The next question, is my object1's instance referenced by other objects? And the answer is yes. And now it invokes the same algorithm on the instance of main activity. Is main activity reachable? And in total, since this algorithm is recursive, my object1 and my object2 instances will be reachable if main activity instance is reachable. And under normal conditions here means that you don't do anything bad with your code. So under normal conditions, activity objects are reachable until after Android invokes their onDestroy callback. So until activity's onDestroy returns, activity object is reachable, and all the other objects it references, even transitively, will also be reachable and will not be cleaned by garbage collector. An interesting edge case in this situation is circular references. So let's say we've got two objects that point to one another. If garbage collector algorithms will be totally naive, it will get into infinite loop between these two objects. But garbage collector is not that stupid, and in this specific case, if there are no other references to either of these two objects, then both of them will be considered unreachable and will be eligible for garbage collection. And garbage collector can handle circular references involving many more objects. So regardless of how many objects are there in a circular chain, garbage collector will understand that these objects basically point to one another, and if there are no external references to that group of objects, all of them will be considered non-reachable and their memory will be reclaimed. And given the fact that you've got a finite amount of memory available for your application, the general rule of thumb is that all objects in your application must be garbage collected eventually. And the only exception to this rule would be if you want specific objects to stay around and being used for the entire lifetime of the application. You want to keep these objects in memory basically forever. However, these objects are the exceptions, and there should be very few of them in your application. Now that you know about garbage collector in Android applications, we can discuss a topic which is absolutely important for all Android developers. That's memory leaks. So memory leak is a term that describes a situation when you have some object which will never be used by the application again. However, it can be garbage collected, so it claims some memory which won't be released ever. And to understand why memory leaks occur, let's get back to object reachability once again. So we have already discussed the algorithm that garbage collector invokes to determine whether some object is reachable or not. And as you might remember, this algorithm is recursive. If you try to imagine this algorithm in real action, then you will understand that any object in your application can be reachable only if there is a chain of references from some root to that object. And I intentionally didn't want to get into what roots are in the previous lecture. Now, however, we need to understand this concept. So roots are basically objects which are always considered reachable, and therefore they will never be cleaned by garbage collector. And just like before, the concept of roots is best understood in its visual form. So imagine that we have the following situation inside application's memory. We have these groups of objects, some of them long, some of them short, some of them have circular references, some of them don't. And the green circles on this diagram are roots. So these are the objects that garbage collector will never clean on its own. And if you apply reachability algorithm on this situation, you will see that objects that have some chain of references from roots are not eligible for garbage collection because roots aren't eligible for garbage collection. And all other groups of objects which don't have any kind of references from roots, even if they have circle references inside the groups themselves, so these objects that aren't referenced from roots, they are non-reachable, and therefore garbage collector will clean them. So roots are the objects that basically hold other objects in memory. And now let's discuss the most important roots in Android applications. First, objects referenced from static fields. So one of the most common sources for memory leaks in Android applications, or at least what used to be one of the most common sources in the past, are static references to activity objects. So basically people would somehow reference activity from static fields, and then those activities will be held in memory forever, even after the system called their onDestroy method. And the second type of roots in Android application is basically your custom subclass of application class. And rigorously speaking, application subclasses aren't proper Java roots. However, for all practical purposes, these objects behave like roots in the context of one single Android application. Therefore, the exact distinction between them and real roots isn't that important. So you just need to remember that if you reference something from application class, then that object will be held in memory basically as long as you hold a reference to it in application class. And the third type of roots in Android applications, and that's the type that is most relevant to this course, are live threads. And hopefully you immediately ask yourself, well, what's live threads? Are there dead threads? Glad you asked, let's discuss that. Just like before, we have basically two ways to instantiate and start a thread. And now when you just instantiate the thread, when you call new thread, then this thread hasn't been started yet, so it is not live yet. Then when you call thread.start, the thread is started, and from that moment the thread is considered live by the system. Therefore, whatever objects this thread references by itself will be held in memory and will not be eligible for garbage collection. Then at some later point in time, thread runs to completion. Basically, its run method returns. And when this happens, the thread is basically dead. It can't be restarted again. It's no longer considered garbage collector root, and the objects that the thread references can be garbage collected if they don't have any other references pointing to them. So in general, from the moment the thread is started and until its run method returns, that thread is considered root, and all objects referenced by that thread are reachable. And two very special kind of references that you need to be aware of if you want to write high quality Android applications that don't have memory leaks are references from anonymous and inner classes to their parent objects. So basically, if we have anonymous thread, which is thread that isn't given a name, it's just instantiated and started, This thread will have implicit reference to the enclosing instance of main activity. And it's not something special to threads. Any anonymous inner class will have an implicit reference to basically the enclosing object. So in this specific instance, main activity instance can't be garbage collected as long as the anonymous thread instance is live. So for as long as this thread takes to execute, garbage collector won't be able to basically claim the memory associated with main activity. And if this thread runs forever, well, then main activity will be leaked forever. And the situation is very similar for inner classes and specifically for inner threads. So if we have like inner thread and we instantiate and start it, this thread will again have an implicit reference to the enclosing instance of main activity. And as long as this thread is live, garbage collector won't be able to clean the memory associated with the enclosing main activity, even if that activity is not in use anymore. For instance, its onDestroy method has already been called by the system and another activity is being recreated instead of it. For example, if you rotate your phone, as long as this thread is alive, the old instance of main activity will hang around, and if the run method of this thread never returns, then basically I've just leaked my main activity forever. And a general rule of thumb in this context is that all started threads in your application must terminate in a timely manner to prevent memory leaks. Now, what does it mean to terminate in a timely manner? Well, it depends on your requirements. It might even be the case that for some threads you decide, okay, this thread, I want it to be live. I want it to run for as long as the application is alive. That's alright if that's your explicit decision and you understand all the implications of that decision. What this rule of thumb basically says is that you need to understand when exactly each thread in your application will terminate, and then basically analyze the implications memory-wise of this thread being live to that point until it is terminated. And again, the exception to this rule will be like threads that you explicitly want to keep around. So just like I said, if you want some thread to be alive for the entire lifetime of your application, that's totally alright as long as you understand what you do. We concluded the previous lecture with the statement that all threads in your application must terminate in a timely manner. And now it's actually the time to understand how do you do that. How do you terminate your threads? To remind you, a thread becomes dead after its run method returns. In other words, to terminate a thread, you need to cause its run method to return. And there are four main ways to achieve that. The first and the most straightforward approach is to just let the code that you have in your run method to complete successfully. And after that, run method will naturally return and the thread will be terminated. The second approach is to return from run method in response to internal error. Then you can return from run method in response to externally set flag. So basically you have a thread and some entity, external entity, sets some kind of a flag and thread terminates in response to this event. And the fourth method is to return from run method in response to thread interruption. Let's discuss each one of these methods in a bit more details. So, successful execution. Let's say we've got this main activity that instantiates a new anonymous thread, and inside this thread we basically do two things. One, fetch some items from endpoint, and then after we get these items, we want to insert them into our local database. So two actions, and the reason why we want to do that on a standalone thread is because both of these actions can take a considerable amount of time, and we wouldn't like to let these actions interfere with other processing in our application. So we start a new thread. However long these two actions will take, after both of them complete, run method will return naturally and this anonymous thread will be dead afterwards. One interesting thing to note here is that inside this anonymous thread, I'm using fields of the enclosing main activity. And that's only possible because this anonymous thread has implicit reference to the enclosing object. In this case, that might not be a problem because, like these actions will take 5, 10 seconds, 15 seconds, and then this thread will be dead and the activity will become eligible for garbage collection. But that's not always the case. Sometimes you might have some process inside your thread that can actually take a lot of time, or maybe it will never complete. In these cases, the thread will basically hold on to this activity indefinitely and it might cause memory leak. All in all, it's alright to let your threads run to successful completion. However, just make sure that it won't cause any troubles. The next approach that you can employ is to terminate on error. So again, we have main activity and anonymous thread inside it. And please note that now this fetch method that we call can throw IO exception. It can happen, for example, if there is no internet connection. In this case, if this fetch failed, you don't want to continue to insertion of the items into your local database. So you short circuit the execution and basically return from run method on error. Once run method returns, this thread is considered dead and there are no risks associated with it anymore. The next on our list is termination due to externally set flag. And the setup is very similar to what we had before, but now we have this fetch aborted flag. And of course you are wondering now, what is this atomic boolean thing? We will discuss atomic stuff later in the course. For now, it's enough that you basically think about this fetch aborted flag as a simple boolean that initially has value of false. So inside run method, after the fetch is completed, we check the value of this flag, and if this flag is true, we again short circuit and return from run method without inserting items into the database. In other words, if any entity in our application will change the value of this flag to true, then this thread will short circuit and return from its run method without executing all the code. One very interesting and tricky thing to note here is that if this flag is changed after the thread passes this if check, then this will have no effect whatsoever. So you need to keep in mind that changing the value of this flag doesn't necessarily mean that the operation will be aborted. It might be the case that you change the value of this flag and the operation still succeeds. And the last approach to threads termination is interruption mechanism. So we have a very similar setup, but now I actually store the reference to the newly created anonymous thread in activities field. And the reason why I do that is because to interrupt a thread, I need to have a reference to it later. So if any external code would like to interrupt this thread in the future, it will basically need to grab this reference and call interrupt on it. Inside the run method, I check the value returned from thread.interrupted static method, and if the value is true, then I short circuit the execution and return from run method. And note that this code inside run method is very similar to what we had before with externally set flag. And indeed, in some sense, externally set flag and thread interruption are two similar mechanisms. However, thread interruption in practice is much more nuanced and complex mechanism. And therefore, I recommend that you always favor externally set flag over thread interruption. And the reason why I recommend that is because thread interruption is indeed very nuanced mechanism. You need to understand it in great details to use it and not make a mistake. And let me show you one example. I want to basically see whether the OkHttp library, which is probably the most widespread library in Android development, so I want to see whether this library interrupts the threads internally. To do that, I execute the following commands, and you can repeat that after me. And then I see that there are basically 4 calls to thread.interrupt method inside OkHttp. And note that all of these calls aren't actually new thread interrupts. They are used to just retain interrupted status on an already interrupted threads. And you don't really need to understand what does it mean to retain interrupted status. The reason I show you this example is to show you that if OkHttp, which is basically the most widespread and highly concurrent library for Android development, if this library doesn't use thread interrupts almost at all, then chances are that your application doesn't need threads interruption either. So you can write highly concurrent, high quality code without ever using threads interruption. And that's exactly what I recommend you to do. So whenever you want to cancel some asynchronous task inside your application, favor externally set flag over threads interruption. And now it's time for you to practice what you've just learned in exercise number 2. So open exercise 2 package, and here you find exercise 2 fragment. This fragment is relatively simple. In its onCreate view, it allocates some dummy data, basically byte array of size 100 megabytes, and then in onStart, it calls to this countScreenTime method. Inside this method, we create a new anonymous thread, and in its runnable, we basically do the following. So initialize screen time seconds to 0, and then loop sleep for 1 second, and after that increment screen time seconds. And then just simply log the result. All in all, this thread simply counts the time in seconds passed since it has been started. Now, the interesting thing to note here is the usage of this thread.sleep method with 1000 milliseconds as a parameter. This method basically says to this thread, now go to sleep, don't do anything for 1 second. And after 1 second, the system will awaken this thread and it will get back to executing the code that follows this sleep call. Now, this sleep method throws interrupted exception. And that's part of threads interruption mechanism that I recommended you to avoid. So in this case, I simply return from this runnable if interrupt is thrown. However, this should not happen because I'm not going to interrupt my threads. So you can basically ignore this interrupted exception and treat it as a boilerplate in this case. Alright, so this fragment basically counts the seconds since it has been started. What's the problem? Well, let me show you what's the problem. Let's run this application. And when it starts, go to exercise 2. So this screen is blank. That's alright because this fragment doesn't have any UI. Now what you can do is go back to your IDE and basically go to Logcat tab. So in Logcat you will see that it actually prints the time it spent on this screen. So everything works alright. The problem is that if I go back and then I again go to exercise 2 fragment, we will see 2 times being printed. So evidently having 2 streams of time in Logcat is a problem. And furthermore, if I keep coming to this exercise 2 fragment and going back, then at some point I will get the application crashed, and then if I look into my Logcat, I can see this threaded out of memory error. So with this exception, the system tells me that it tried to allocate 100 megabytes, but it didn't have this memory available, and in response to that, it basically shut down my application. And this out of memory exception will always be thrown when your application exceeds the maximum memory available for it. So all of that shows us that there is memory leak in my application. And your goal in exercise number 2 will be to fix this memory leak. So you open this exercise 2 fragment and you notice that basically the memory leak stems from the fact that this anonymous thread is never stopped. It runs indefinitely. And since it has a reference to the enclosing object, exercise 2 fragment in this case, this fragment will be kept in memory forever, and this dummy data, 100 megabytes that I allocate in this fragment, will basically never be released and eventually will cause out of memory error to be thrown. To fix this issue, you need to basically terminate this thread when system calls fragments on stop method. And the way to do that is to use externally set flag. So just like I've demonstrated you in the previous lecture, you use atomic boolean, and you don't need to understand what's atomic boolean right now. Just use it in exactly the same manner that I showed you. And whenever the system calls on stop, you should set this atomic boolean to false, and then you need to make this code inside the run method complete and the method itself return. That way the thread will become dead and we will avoid memory leak. Now, if you feel that these exercises are a bit artificial and don't reflect your actual use cases inside real Android applications, then you're absolutely right. The reason for that is because it's very difficult to come up with exercises that will, on the one hand, let you practice something that you learned just now, and on the other hand, wouldn't be too advanced and wouldn't contain too many new concepts at once. So please just concentrate on this exercise, do it, and don't concentrate too much on a question where in a real Android application would you use something like that. Most probably you wouldn't. This exercise is just for you to practice to terminate your threads. So good luck and have fun! Alright, it's time to summarize this module and our discussion of threads so far. So, thread class in Android represents single in-process thread of execution. In other words, a single thread in Android application corresponds to a single CPU concurrent task. But it's not enough to just instantiate threads. When you instantiate thread object, it's not started yet. So don't forget to call start on all your threads. After you start any thread, it immediately becomes garbage collection root. Therefore, objects referenced from live threads will not be garbage collected, and that's important to keep in mind to prevent memory leaks in your Android application. And don't forget that instances of anonymous and inner classes have implicit references to enclosing objects. So if you don't see a reference, it doesn't mean that it's not there. And it's very easy to forget about implicit, invisible references like this. Therefore, be exceptionally aware of this aspect of Java virtual machine operation. The corollary of the fact that live threads constitute garbage collection roots is that all threads in your application must terminate in a timely manner. Now, what timely manner means exactly is up to you. You know the requirements of your application, and you are in position to define when exactly each thread will terminate. And as I said, if you understand what you do and you understand your requirements, then it's totally alright to let some threads live forever. Just make sure that you don't shoot yourself in the foot with this approach. In this module we covered a lot of material, really, and hopefully you enjoyed doing the exercises. However, these were just the basics. There is a lot more to be said about threads in general and how to handle multi-threading in Android specifically. Now, I am sure that you are very excited about the prospect of learning a lot more in the future lectures. In this and the following lectures, we are going to discuss user interface thread, or in short UI thread, in Android applications. Now, I'm sure that most people who will watch this course will already understand what's UI thread, because it's one of the first concepts that Android developers learn. However, just for completeness and to make sure that we are all on the same page, I want to cover the most important concepts that you need to know in order to work safely with UI thread in your application. So, UI thread is a special thread started by Android framework and associated with a single application. In other words, whenever your application starts, Android framework automatically creates a new thread for it, and this new thread becomes your UI thread. The main characteristics of UI thread are as follows. First, it's started by Android framework when your application starts, so you don't need to do anything to get this thread instantiated and running. After it is started, UI thread lives for as long as your application lives. So it's terminated only when application's process terminates. Whatever it is that needs to be drawn as application's user interface, all of that is taken care of on UI thread. In addition, all lifecycle callbacks like onStart, onStop, etc. are executed on this special thread. Furthermore, whenever user interacts with the user interface, for example, clicks on a button and then onClick method is called, all of these event handlers are executed on UI thread as well. And last but not least is that if you, as a developer, want to change anything about user interface of your application, all of these manipulations must be performed on UI thread. There are two alternative names for UI thread. So it's either UI thread or sometimes it's called also main thread. And to be absolutely rigorous, I must tell you that UI thread and main thread are not necessarily the same thread. There are situations when these threads will be different. However, this distinction is irrelevant to Android application developers, and for all practical purposes, UI thread and main thread are the same thing. And if you do want to understand the difference between UI thread and main thread, then I will link to my answer on Stack Overflow that describes that difference. However, maybe it's not the best idea to read it right now, because it's kind of irrelevant and very low level. So maybe a better idea will be to complete the course first and then get back to this answer if you still will be interested in it. And once we understand what's UI thread, we can also define a background thread. So background thread is any thread in your application that is not UI thread, as simple as that. The goal of this short lecture is to simply convince you that all the lifecycle callbacks and event handlers are indeed called on UI thread of your application. So to do that, I wrote this UI thread demonstration fragment. And it's very simple. Basically, I have a bunch of callback methods here overridden, and in each one of them, I call this log thread info method and pass in the name of the callback. And inside this method, I simply log the name of the event that took place, and then I call thread current thread, which will return me the current thread of execution, and I log its name and I log its ID. In addition, this fragment has one button, and when I click that button, I again call the same method with the name of button callback. So let's see how it works. The application started, and I can go to UI thread demonstration entry, and now in logcat I can see that these lifecycle events were called on create, on view created, on start, and then on resume, and all of them were called on a thread named main. So main thread and UI thread are basically the same, and thread ID is 2. And it doesn't really matter which thread ID is assigned to your UI thread, but from what I've seen, usually it will be either 1 or 2. So all the positive lifecycle callbacks were called on UI thread, and then I can click on this button, right? And I can see that it also, event button callback, and then main thread ID 2. So click event handler was called on the main thread as well. And the last, I can go back to my home screen, and then I can see all the negative callback methods. So on resume, on stop, on destroy view, and on destroy. And all of them are called on the same thread. So this was just a short demonstration of how can you know that all of these callbacks are indeed called on UI thread. And if you want to check some other events in your application to see whether they are called on UI thread as well, then you can just basically do the same exact trick and log the name of the currently executed thread. Let's talk about user interface responsiveness now. Responsiveness in this context is the perceived smoothness of your application by your users. The general limitation in Android applications is that if you do too much work on your UI thread, your application will become less responsive. Let's understand why that is the case. So Android applications are required to provide a specific level of responsiveness, and this stems from the fact that they should render 60 frames per second on device screen. If you think about it, it means that each new frame should be rendered in 60 milliseconds. And since all UI manipulations, including the rendering, take place on UI thread, if you consume too much time on that thread, then this thread might not be able to provide new frame every 16 milliseconds. Therefore, your code shouldn't execute on UI thread for longer than few milliseconds. Now, it's impossible to say exactly how many milliseconds you can execute on UI thread because it depends on many factors. But a good rule of thumb in this context is that if you think that some piece of code can potentially execute for even 1 or 2 milliseconds, then it's worth being careful and not execute that code on UI thread. However, all of us do mistakes, and therefore inevitably sometime in the future you will put a code that shouldn't run on UI thread to run on UI thread. And when this happens, you will see the following warning signs. First of all, whenever you do too much work on UI thread, your user interface responsiveness degrades, so you can see freezes or maybe non-smooth animations and other visual artifacts. In addition, Android will notify you whenever your application can't provide the required level of responsiveness. So if you remember, in exercise number 1, I put something that ran for 10 seconds on UI thread, and then we've seen this entry in logcat. Skipped 611 frames. The application may be doing too much work on its main thread. And if you multiply 611 by 16 milliseconds per frame, you will arrive approximately at the same 10 seconds. So whenever your application does too much work on UI thread, which causes skipped frames, you will get this notification in your logcat. So look for them. And in the most extreme cases, when you stack your UI thread for seconds, you can get this application not responding error and your application will crash. So look for this in your analytics. All in all, you should aim for 0 skipped frames in your application, and that's one of the most fundamental quality standards of Android applications. Now, don't go too crazy about that, because there are very low-end Android devices out there. So on these devices, your application can skip frames and maybe you won't be able to do anything about it. But users on these devices are usually also accustomed to applications not performing in their best. Therefore, just test your application on reasonable devices and make sure that it doesn't skip frames there. And the immediate corollary from this discussion is that all time-consuming operations should be offloaded to background threads. And this is a very important rule to follow in your application. In the previous lecture, you understood why it's important to offload all potentially long-running tasks to background threads. However, there is one more complication associated with that. Let me demonstrate you this complication now. So I will go to our tutorial application, and then inside Screens Navigator class, I will basically replace exercise 1 fragment with solution exercise 1 fragment. Basically, I want to show you the solution that I built. And I will go to this solution exercise 1 fragment. And let me remind you what it does. So basically it has one button count iterations. And when you click on it, it offloads to background thread a simple task that basically loops for some predefined amount of time, which is 10 seconds in this case, and then logs some entries. So basically it says iteration in seconds, etc. So now I would like to change that a bit, and instead of logging this information, I would like to display this information on the same button that I clicked before. So instead of log call, which I will remove, I add the following: button count iterations, set text, and then let's say iteration, and add iterations count. And of course that's not correct, so iterations count. And now let's run this application. After the application starts, I click on exercise 1 entry, which leads me, just to remind you, to solution exercise 1 fragment. And inside this fragment, I find this count iterations button and I click on it. The application runs, but does not print anything into the logcat. See? And let's wait for a little bit more time. And the application crashes. Let's see what the problem was. Called from wrong thread exception. Only the original thread that created a view hierarchy can touch its views. So basically what Android tells us is that only the thread that created the views inside my application should modify them in any way. And recall that the thread that creates views in Android is UI thread. So basically what this error says is that you should modify your views only on UI thread. You can't perform these modifications from background threads as I did in this example. And that poses a question. How do we transfer the execution from background thread back to UI thread? This will be the topic of the next lecture. The goal of this lecture is to show you how to transfer the execution from background threads back to UI thread. To do that, I created this UI handler demonstration fragment, and you will understand why it's called UI handler in several minutes. Currently, this fragment is simply a copy of solution exercise 1 fragment, the same fragment that we reviewed in the previous lecture. Now, however, I do really want to show these execution results on the UI of my application instead of in logcat. So I'll remove this, and to remind you, something like this, button count iterations, set text, and something like iterations and iterations count. So statement like this executed from background thread will lead to my application crashing at runtime. To resolve this issue, I'm going here, and here I define a new field of type handler, Android.OS handler, and I call it UI handler. And I initialize this handler to new handler, and as a parameter I pass in looper get main looper. Currently you don't need to understand what handler and looper are. Just treat this code as some kind of black magic, which results in me having an object which I can use in my code. So after I have this UI handler object, I can go here and do the following. UI handler post new runnable. So UI handler has this post method, and it accepts runnable objects. And inside this runnable, I will put this code that resulted in exception when executed from background thread. Now it resides inside runnable that is posted to UI handler. However, there is a problem. And the problem is that this variable, iterations count, is accessed from within inner class, needs to be declared final. And that's just how Java memory model works. So the compiler basically says the following. If you have a variable, like iterations count in this case, which is scoped to some method, run method in this case. So you have this local variable inside the method. If you want to access this variable from within inner class like I do in this case, because this anonymous runnable is an inner class, well, if I want to access this variable, it tells me that it must be final. And I can't really make it final because this variable is incremented inside this method. However, what I can do is define additional variable, and this one will be final indeed, and then call it, for example, iterations count final equals iterations count. And here, instead of using iterations count, I will use iterations count final. Again, that's just how Java memory model works. In order for local variables inside methods to be accessed from within inner classes, they need to be defined final. And in this case, I simply created additional helper variable to be used inside this inner class. Let's run the application and see what happens now. After the application starts, I go to this UI handler demonstration screen, and I have a count iterations button here, and I click on it. After that, I need to wait for 10 seconds for the results. So let's wait a little bit. And voila, you see the text of this button changed to what I wanted it to be, iterations and the number of iterations in 10 seconds. So once again, what I did here. I started by adding a new field to this class of type handler, and I call it UI handler in this case. And the way I construct this handler is just that. You don't need to understand why I do it like this at this moment. And once I have my handler, I can go into this method and use this handler to post a new runnable to it. And inside this runnable, remind you, runnable is kind of a wrapper for code. So inside this new runnable, I can actually access my UI and change its state. So once runnable is posted to UI handler, I can perform UI modifications. And why is that the case? Why I can perform UI modifications from here while I couldn't perform them from here? Well, let me show you something. Let's say that I want to log UI handler. And what I want to log? Well, I want to log the following: current thread, and then thread, current thread, get name. Now I will run the application again. Just like before, go to UI handler demonstration and click on count iterations, and then wait for 10 seconds before the results are available. And just like before, the UI reflects the number of iterations that could be performed in 10 seconds. But in addition, I also have this entry in my logcat. So UI handler current thread is main. And I remind you that main thread and UI thread are basically the same thread. So as you see, by posting new runnable to UI handler, and to remind you, UI handler is a special object of type handler that gets main looper as constructor argument. So by posting runnables to UI handler, I basically transfer the execution back to UI thread. And that's, ladies and gentlemen, how you ensure that your code executes on the UI thread of your Android application. In the previous lecture, I introduced to you handler and looper classes in Android. The goal of this lecture is to provide you a little bit more intuition about these constructs. So to do that, I created this new fragment, custom handler demonstration fragment. And currently this fragment is very simple. It has just one single button send job. And when this button is clicked, send job method is being called. Now, this method is completely empty at this point, but I wanted to do the following. Each time when send job method is called, I want to execute some long-running process. And since we are talking about long-running process, I need to offload it to background thread. We know that already. However, there is one additional requirement. If the user clicks on send job button multiple times, I want to send multiple jobs, and I want to remember these jobs, and I want to execute all of them one by one on the same thread sequentially. So how do I do that? Well, the very first thing that I will need is a thread. But I don't want to instantiate this thread inside send job method, because remember, I want to have one thread for all the jobs. Therefore, what I will do, I will come here and basically override onStart method. And inside this onStart method, I will write init worker thread. And inside this init worker thread method, I will do the following. You know this code, right? New runnable. And currently I'll keep this runnable empty. And then I don't forget to start this thread. So what should I do inside this runnable? Recall that my goal with this fragment is to basically pass into this runnable new jobs and make sure that they all execute on this thread. So I need some mechanism that will allow me to inject jobs from outside. And this mechanism is called blocking queue. Now, we haven't really reached the point in this course when we can discuss blocking queue in details. Therefore, at this point, just treat blocking queue as some kind of black magic. So, private final blocking queue of type runnable, because that's what my job will be. It will be runnables, and I will call it simply queue, and it's equals new linked blocking queue. Alright, now once I've got this queue, I go back to my run method and I say the following: while true, so loop forever, I want to take some runnable object from my queue. And the way to do that is to call this take method. Now, this take method immediately tells me that it wants to throw interrupted exception. So I surround it with try and catch and simply return here. And I remind you that I allow myself to simply return from this method on this interrupted exception because I'm not going to interrupt this thread ever. So this exception will never be really thrown and I can just treat it as a boilerplate. Alright, so now I want to access this runnable from the outer scope, not from try catch block. So I will do it like this. And now here I want to call runnable.run. What this means is that we will take runnables from this queue one by one, and then we will call their run method. And since this run, external run method of this runnable will be called on a background thread, one single background thread, then basically all runnables that I post into this queue will be executed on this one single background thread as well. Now, the thing about take method of blocking queue is that it is blocking. That's the reason why blocking queue is called blocking queue and not just simple queue. And blocking here means that if this queue is empty, then this take method will basically pause the thread of execution until anything is available inside this queue. So if this queue is empty when I call take, then this line of code will cause my thread to basically sleep until something is available inside this queue again. And if there's anything inside this queue already, then I will simply get this element and the execution will proceed to running it. Alright, so now I have this loop that loops forever and executes runnables. How do I stop it? The best approach to stop this kind of worker thread that works with blocking queues is to use poisonous data. So what I mean is that I will have here private static final runnable, and I call it poison, and that will be just new runnable, and I can like keep it absolutely empty. And now if I want to stop my worker thread, I want to basically post this runnable, this poison data into my queue. And the best place to do that is of course in onStop. So I override onStop, and here inside onStop I do the following: my queue add poison data. And once I pushed poison data into the queue, I can go here inside my worker thread and say the following: if the runnable that you took from the queue equals poison data, and this equality is comparison by reference, then basically I know that it's a command to stop. So I just return from this run method execution, and therefore this will cause this thread to become dead. Until now I set worker thread inside this fragment, and I made sure that this worker thread will eventually terminate after onStop is called. Now please notice that it's not guaranteed that this worker thread will terminate immediately when onStop is called, because it might be the case that this queue already has several elements inside, and then I add this poison runnable into it. So before it reaches this point of poisoning and returns, it will need to execute all the elements inside this queue. So what I can do about it is, for example, clear my queue here. And this will ensure that the queue will clear all the current jobs that it holds, and basically the next runnable that my worker thread will see will be this poison runnable, and it will terminate. So this prevents this worker thread to do work after onStop is called. So far great. Now it's time to actually take care of sending jobs to my worker thread. Alright, so go to send job method, and here I, for example, define a new runnable, and that's new runnable. And inside its run method, I want to perform some long running task. And in this case, I define this constant, seconds to count 5. And what I want to do is very similar to what you've seen me doing before. I create a for loop, and here I do initialize I to 0, and then I say I smaller than seconds to count, and then increment I. And inside here I go thread sleep for 1000 milliseconds, which is 1 second. And again, I'm not going to use interrupts, so I can simply return from here. And after this thread was sleeping for 1 second, I want to do what? Well, let's log something. D and custom handler. And then the message in this case will be iteration and I. Something very simple. Okay, so my runnable, my job, okay, let's call it job for clarity. So my job is to basically loop for 5 seconds and print something into the logcat. And once I have this job, I can basically go and post it to my queue, right? So queue add job. And after I add this job to the queue, if my worker thread has been sleeping here at this take method, it will awaken, see that there is a new something into the queue, and will take it out of the queue and then execute it. Well, it looks like everything is alright. Let's run the application and test this functionality. After the application starts, I go to my custom handler demo screen, and here it is, send job button. I click on it, and let's see what's going on. It starts to count iterations. So it should count to 4 and then stop. Alright, and let's clear that. And if I click on send job for 3 times, for example, we should see 3 times counting. So it will go to 4 now, and then it starts from 0, 1, 2, 3, 4, and then again 1, 2, 3, 4. Great. And now if I go back, then my worker thread will be released and everything will be alright. There will be no memory leaks. So far I implemented something that's called worker thread that has a queue of jobs, and this pattern is very popular in concurrent software. However, the goal of this lecture, I remind you, is to give you a little bit more intuition about handlers and loopers. So let me refactor this code a bit, and then you will start seeing the similarities more clearly. So the very first thing that I'll do is creating this new inner class here. It will be a private class custom handler, and inside of the constructor of this custom handler class, I will call the init worker thread method. Now I take this init worker thread and I want to move it to this custom handler class. Great. And I don't want to call init worker thread here. What I want to do here is to define a new private custom handler, call it custom handler, and then I will go to my own start method and say the following: custom handler equals new custom handler. And inside the constructor of this custom handler, I initialize my worker thread. And I can furthermore take this queue, because it doesn't belong to the fragment, it belongs to my custom handler. Now let's fix the errors. In onStop, I don't have the access to the queue anymore. So what I do instead is I call custom handler, and let's call this method simply stop. So create this method, and inside this method I put exactly the same code. Alright, and now this queue add job, instead of doing this, what I want to do is to call custom handler post and job. Now I add this create method post runnable job and move this code into my custom handler. Okay, and I furthermore can basically do it like this. Don't really need this, right? So new runnable and do that. And the last thing that I need to do is to take this poison data. And again, it doesn't belong to the fragment anymore. It belongs to my custom handler. Can't be static here, no problem. I don't really need it to be static, and I can just make it like that. So now everything related to basically this worker thread and its management is enclosed within this custom handler class. And the external world, for example, this custom handler demonstration fragment, all it knows is about its API. So it instantiates a new custom handler in onStart. And in onStop, then it basically stops this custom handler. And in sendJob method, it invokes post. If we go to UI demonstration fragment, UI handler demonstration fragment, that's exactly what I did here, remember? So whenever I wanted to post something to UI thread, I called this MUI handler and I posted some runnable to it for execution. It's exactly the same API that I have here in my custom handler demonstration fragment. And the only difference is that I instantiate my custom handler here inside onStart and I stop it in onStop. And the only reason for that difference is because UI thread is not instantiated by Android developers. I don't instantiate it. Android framework instantiates it when the application starts. You should remember that, we discussed it. And then this UI thread lives for as long as the application is alive, and it's terminated only when application is going to die. So I need this and these calls only because I have a worker thread that I myself manage. UI thread is managed by Android framework for me. Therefore, UI handler doesn't have these requirements, and I can simply instantiate it and post runnables to it. So that's what handler is. So handler is simply wrapping around some thread, and this thread is called worker thread, or you can call it looper thread, because it basically loops forever. Okay, as long as it's not stopped, it loops. And that's why when I instantiate this handler, I pass in main looper. So main looper is basically some abstraction over main UI thread, which is basically just loops over runnables that either you or Android system posts to it. And this pretty much summarizes all you need to know about handler and looper, because even though you can use Android handlers with threads other than UI thread, I absolutely recommend you to avoid that. In my opinion, neither handler nor looper are appropriate constructs to be used in our Android applications. So the only way you use handler in your application is to do that, and then post something to UI thread, because that's the only way to access UI thread. You can't do it differently. So you do need this handler, and you do need to pass main looper into it. However, other than that, you don't need to know anything about handler or anything about looper. But if you are interested to basically understand more and maybe review their code of handler and looper, I will link the source code of these two classes in AUSP Android open source project to this lecture. And these classes aren't very big by any stretch of imagination. So if you are curious how they're implemented inside, you can actually go and review that code. However, as I said, it's absolutely not mandatory. You shouldn't use handler or looper in your applications other than for this one single purpose, to post runnables to be executed on UI thread. In the last couple of lectures, you learned a lot about UI thread and handler and looper. Now it's your turn to work with these classes and practice what you've learned with exercise number 3. So go to exercises package, exercise 3, and open exercise 3 fragment. This fragment is very simple. It has just two elements, button and a text view. When the button is clicked, count iterations method is called. Currently this method is empty, and that's exactly where you should put your code. What I want you to do in this exercise is implement seconds counter again. However, this time, instead of logging the progress into logcat, I want you to show the progress on the screen. Furthermore, I want you to make sure that there will be no multiple tasks running at the same time. To achieve that, you need to implement the following logic. I described it here in this command. So first of all, you need to disable the button to prevent multiple clicks on it. Then you need to start counting on background thread using some loop and thread.sleep calls. As the counting progresses, I want you to show the current count inside text view. And then lastly, when the count completes, show done text in text view and then enable the button back. So you should be able to click on a button, see the counter on the screen, and then see done. Once you see done, the button should unfreeze, and then you should be able to click it again to count again. And once again, in a real Android project, you probably wouldn't implement counter in this way. However, you need to practice offloading tasks to background thread and then returning the execution to UI thread. And this exercise will achieve that. So please don't overthink where exactly would I use this thing in my real Android applications. Probably you wouldn't, but that's not the point. So good luck and have fun! I hope you enjoyed learning about UI thread and doing the exercise. Now it's time to summarize what you learned in this module. So UI thread is a special kind of looper thread that Android framework starts for each application. And looper here means that this thread basically loops forever and processes runnables that are sent to it. And again, it's either we can send these runnables from our code or Android framework sends its runnables, for example, to call Lifecycle methods. So all of that takes place on UI thread, and this thread lives for as long as your application is alive. Based on the discussion in this module, I think we can distill several rules of thumb for working with UI thread. So the very first rule of thumb, which is very important, is that you shouldn't perform any long-running tasks on UI thread. And while it's difficult to say what long-running means and it depends on the context, as a rule of thumb, if your task takes longer than few milliseconds or it can potentially take longer than few milliseconds, then you should offload those tasks to background threads. And then after you offload tasks to background thread, if you need to perform any kind of user interface manipulations, then you should return the execution from background thread to UI thread. And in general, the main objective when working with UI thread is that your application doesn't skip any frames. And you have several warning signs that you should watch for, and these warning signs will alarm you ahead of time that there might be some problem and that your application's user experience might suffer because you do too much work on UI thread. So look for these signs. And while it's important to understand that offloading tasks to background thread is important and even mandatory practice, most of your application's code should execute on UI thread. And when I say most of the code, I mean the lifecycle callbacks and the interactions with UI, in fact all UI manipulations whatsoever, and navigation between screens, etc, etc, etc. There's really a relatively small subset of tasks that might take a long time to execute that you should offload to background threads. So just remember that whenever you need to decide on which thread to execute your code, UI thread should be the default choice, unless you have reasons not to do that.